So we'll start from where we left yesterday. So this was the last thing we seen in yesterday's class, right? We said that we're going to use multiple filters. We will be having multiple representations of input image, and that multiple representations further processed and fed into classifier. Now, before actually we move proceed, it's important to know how to do some manual calculations. This is important not only when you will be crafting the network, but also it is required if you want to do some quick sanity check whenever you have built a big network. Okay. So in here you see you are having an input image, and the dimension of that input image is 27 cross, sorry, 227 cross 227 cross 3. That's not 277, it's 227. Let me make that correction. 227. Okay. Kernel is 11 cross 11 cross 3, right? And number of kernels that you're going to use for this convolution operation is 96. Stride is 4, and we're not going to do any padding here. So you have to tell me, after doing these operations, the output which you'll be getting here, what would be the dimension of that output? So if you recall, this was a formula we said, right? This is the formula we have seen in previous class. And this formula says that if I know the dimension of my input image, if I know the dimension of my kernel, if I know the padding, and if I know the stride, I can compute the dimension of my output. Okay. So here, if you see 227 plus what is my dimension of kernel, 11. I'm not going to use any padding here. And what is my stride? Stride is 4. So what is this? Right.
Also, can you remind us what the stride stands for?
Okay. For that, I think I need to go back to the previous slide.
Is it layers or something?
No, it's not. It is not connected to layer. So yeah, I think this image is perfect. So see, we are putting our kernel here, right? In this input image. After that, what I said is you have to move this kernel by unit 1, first of all horizontally and then vertically, right? Now, yesterday we agreed that we need not to move this kernel by unit 1. We can move it by unit 2, 3 also. So that is precisely called stride. Stride is the number of steps that you will be taking jump to move this kernel leftward and downward.
Okay, yeah, it's clear now. So S equal to 4 means we are jumping 4 steps and going to the 5th pixel.
Yes. Now, if I'll take a stride here 4, right? So in the next iterations, I'll be putting my kernel like this. 1, 2, 3, 4. I should put my kernel here.
So the fourth pixel will be part of the kernel. It will not skipping that 4th pixel and going to the 5th one, right?
Yes.
The way you're showing here.
Yes.
The 4th pixel is included in it. Okay.
Yes. See, when we took stride equal to 1, the position of my kernel was like this, right? My kernel was this.
Yeah.
So when it is stride equal to 4, then from 1, 2, 3, 4.
Okay.
Okay. So this is a calculation for computing the output. Okay. So here if we'll put the values in formula, right? Can you do this quick calculation? 227 plus 11 is 238. 238 divided by 4.
4 5 now.
Okay, so instead of this, I think this would be something different. This input is something different. 227 plus F.
Point something.
Yeah, it should be a discrete number. It should not be in decimal.
238. Okay. 238. That is 50.
It should be 216. Like if you divide, right?
216. No, 216.
No, I'm saying 54 into 4 is 216.
54 into 4 is 216. So 216, if it 216 minus
11.
11. Yeah.
205.
Yeah.
Divided by 4.
Yep.
So it's a 205 by 205 matrix then, right?
Yes. So this way, so this my input would have been having this dimension. I'll apply this formula and I'll compute the output, the dimension of the output layer. But the formula is correct. The value may not be matching here,
Okay.
but this is the formula. Okay. Can you try for this one? Let's try for this one.
300.
300. What is my F here?
5.
5. Am I applying padding here?
No.
Yes. So padding is 0 divided by
5.
5. 305 divided by
61. That is
61. Okay. So the formula is not this one. Let me check this. I think this is
so what is this K equal to 30?
K is equal to number of kernels. So I said that you will be applying multiple kernels over the same image, right? Wait. Let me check the formula once.
But it is not 30, right? I mean, if I multiply 5 into 3, or
Yeah. This is a formula. I was putting the formula wrongly. Wi plus 2p minus f upon s plus 1.
okay.
So the formula is Wi plus 2p
2p
minus f upon s plus 1. This is the formula. Okay. This is garbage. What
So
is
then
my Wi? Wi is 300.
Yeah, 300 plus 0.
Plus 0 minus f. F is 5 divided by s. S is what?
5.
S is 5 plus 1. Right? This will be 60.
95.
Right?
That will be 60.
Not 60. Not 60.
295 divided by 5.
59 plus 1, 60. Yeah. That is
That's
60.
59 plus 1 is 60. Okay. Now let's do this calculation for this one. 227, right? Plus 0 minus f. What is my f? 11 divided by 4 plus 1, right? 216 divided by 4. 4 5 are 20.
260.
4 4 is 16.
54. Yeah.
Plus 1. So it should have been 55. Okay. You understood the calculation, right?
Yeah. But then one question I have is in the options, right? We are getting one value, 60. So that is telling us that both the dimensions are 60 cross 60 and the
Yes.
kernel size, kernel width is 3. We are getting it from F. And that's why
Yes.
the convolution network dimensions are going to be same, like that
Yes.
one, right?
Yep. Yep. See,
So does it also happen that where kernel is like rectangle instead of a square?
no, kernel is also square. This is the depth of kernel. The length and width is 11 cross 11.
No, I know. I'm asking, is it possible that in
No,
scenarios where the kernel length, width and height are not same?
it is possible, but you'll not find anywhere in uh, any of the architecture or any textbook that they have kept a rectangular kernel instead of square one. It is practically it is possible, but it's just that as a convention we prefer to go for square kernel, because ultimately this kernel is going to be a matrix, right?
Yeah.
And lot of matrix computation is specifically defined for square matrix. The condition is the matrix should be square, then you'll be able to compute some matrix operation like computing inverse, computing determinant. All those things are defined only for square matrix, right? So that's why people prefer to keep this kernel as a square matrix.
But input can be rectangle, right?
Input can be rectangular. Yeah, input can be rectangular, but again, in input also we prefer to keep at square matrix.
Okay.
If the input is not square matrix, we do the padding and we try to make it as a square matrix. I understand that the input which are padding, it may not be square all the time, right? But in that case, before we actually apply it to the network, we do some interpolations and we try to bring it as a square matrix. Okay. All right. So convolution operations we have seen. Did I talk about pooling?
No.
Okay. So we'll be seeing today pooling. Okay. So so by now I think you're comfortable that we will be having input in image. We will be applying some filter to it and we'll apply convolutions, and after that we get some output like this, right? Now onwards we'll not call it as output, because this is not output. This is an intermediate output which has to be fed into another layer, and this process will keep on happening for a certain number of times. After that, the final product is called output. That's why the result of this convolution, we'll call it as feature map. This is a standard name. This is a standard terminology for the output we get when we perform convolution operation. This is called feature map. Okay. Now this is my input, and after that, and this is my filter. I applied convolution operation between them. I got this feature map. The next thing that we do is we apply some non-linearity to it. So non-linearity means, again here it will come activation function. Okay.
So why do you're mentioning there that this is typically feature map is typically the same size of input if
Yes.
appropriate padding is applied? What does it mean?
See, okay. So if you recall, we discussed that if you're not applying padding, then the size of your image will keep on diminishing, because I won't be able to apply filter on my corner pixel, right?
Yeah.
So what I'm saying that the size of this feature map will not diminish if I do some appropriate padding. You remember we saw the concept of padding yesterday. We applied some.
Yeah, it's understood now what you mean there.
Okay. So we applied here convolution operation. We got this feature map, and after that we'll apply some non-linearity to it. When I say non-linearity, I mean activation function. So I'll apply some activation function here, right? Typically in case of image, we apply ReLU activation function. Okay. I apply activation function here. After that, what I'll do is, so when I'm applying an activation function, the dimension of this intermediate stage will not be affected. The dimension will be exactly as it is.
I'm sorry, can you repeat?
After doing this convolution operations, I'm getting this feature map.
Yeah.
Okay, and this feature map is having dimension 4 cross 4. Well,
Yeah.
now I will be applying a activation function on top of this. After applying the activation function, again I will have a matrix of 4 cross 4. The dimension of this matrix is not going to change. It's just that individual value might change because I'm applying some activation function.
Yeah.
Right. So now the thing which I get after applying activation function on my feature map, now what we do, we apply here another layer which is called pooling. So for timing, you just consider that my activation function is identity function, which doesn't do anything with this feature map. It will keep the output as it is.
You mean it is not doing anything? Even though we are applying, but it is not doing it.
Yes, for the time being, I'm saying just imagine this. In reality, it doesn't happen so, but just to make the math simple, I'm saying that assume that for now your activation function is identity function. It will just simply multiply each of your value by 1.
Yeah.
Okay. So now we applied activation function on my feature map. The output is this only because we have considered identity function. Now what we'll do is, I might not be interested in all the pixel values. What I'll say that I just wanted to keep those pixel values where the pixels are prominent. Only the important characteristics of this matrix I'm going to keep. So for that, we have a concept of pooling, and in that pooling, what we do is, again, we apply a filter. So here I'm applying 2 cross 2 filter. Okay. And what it does is, whatever pixel value that will fall in this 2 cross 2 filter will take the best value out of it, highest value out of it. Okay. So when I'm applying this max pooling on top of this, I'll be getting a matrix. So first of all, see, out of this 1458, what is the highest value? 8.
8.
Right. So I got 8 here. After that, I'll slide this kernel, right? So again, I'm taking a stride of 2 here. So instead of so I'll be putting my kernel here. What is the highest value here?
4.
4. Then I'll place my kernel here. 7. And this is 5. Okay.
Yeah.
So after applying a max pooling on top of this feature map, I got a reduced output whose dimension is 2 cross 2. Okay. Why I am doing a max pooling here? Because this is further reducing my complexity. I did not to consider all the pixel value. I am only considering those pixel values whose intensity is higher. Okay. Because it significantly reduces my computation. So far, whatever we have seen, we are having an input image, right? After that, I am applying a convolution operation. And once I apply convolution operation, after that, I'm applying activation function. After applying activation function, I'm applying max pooling. This has reduced the dimension of my feature map. Okay. Now, after this, I'll further apply convolution operation. And this process will go on for a certain number of times, and that number we will be deciding. Okay, so this is what typically happens in any convolution neural network. This sequence will follow repeatedly. Okay, so now here we have done max pooling. It's not really required that you always do max pooling. You could have taken an average also. So when I applied this filter, instead of taking the highest value, you can take the average pixel value. So you'll just do the summation of 1458 divided by 4. That will give the average value of it. And that is called average pooling. Okay. Any question in this part?
So the output of after applying the max pooling function, you are applying one more filter, and then the output of that is a smaller matrix.
Yes.
And that is also a convoluted matrix, right?
Convoluted, not actually convoluted matrix. Convoluted matrix is this one, feature map.
So after we are applying the filter 2x2, what with the resultant matrix is called what?
You can call it as a pooled matrix,
Okay.
or downsample matrix.
When you had written when you had written something, I thought you wrote that only, like again the output is convoluted. So
Yeah. See, once you have got this downsample matrix, again you will apply filter on top of this. You will perform the convolution. You will get another feature map. You will again do this max pooling. Again, you will be getting this downsampled matrix. So this process will keep on happening. But I'm talking about the first iteration.
Okay.
Is everyone clear on this part?
Yes.
Okay. Okay. So
But
now,
one question:
Mhm.
how do we decide which pooling we have to choose? Like you said, there are several poolings.
Yeah, that's a good question. So here I would say deciding an optimal polling strategy. So there is no rule of thumb for deciding optimal polling strategy. You'll see most of the architecture that people have already built, like rested 50 inception, V2, V3, all those architecture they uses max pooling, right? So that is a matter of hit and trial thing. We by just looking at the problem statement, we cannot say that in this particular problem this max pooling will work better or average pooling will work better. Right? You have to play around with this strategy, and the strategy that works best for you, you can fix that strategy.
Okay.
But most of the time for architecture, you'll see that max pooling is a very common technique which has worked well and commonly used pooling strategy. Okay.
Yes.
Okay. Now coming to the most important slide, and this will summarize everything. And if you have understood this slide well, then you have really aced CNN thing, because everything that we have learned so far, we are going to sum up. And if you understood this one, you can solve a CNN by using pen paper also. Okay. So pay attention here. Let me know if you face any difficulty at any point of time. This slide will invest some time, probably the entire day it can take just to have discussion on this slide. Okay. Let me. Okay. So this is my input image. Okay. And the dimension of this input image is 32 cross 32. Okay. And since this is not a colored image, so the channel is 1. Okay. So this is my dimension of input image. Now what is happening is I am having a kernel. So first of all, what I have to do, I have to apply convolution operation, right? For doing the convolution operation, I'll be using a filter, and that filter dimension is 5. So this is what 5 cross 5 cross 1. Okay. So when I convolute this input image by a filter of size 5, okay, I'll be getting some output of it. This is called feature map. Just now we have seen.
Yeah.
Right.
Yes.
And I'm following certain configurations. Like in this case, I'll be taking stride equal to 1. That means I'm not jumping over any pixel. I'm just doing it pixel by pixel. I'm not using any padding. Since I'm not using any padding, this is obvious that the output which I'll be getting after convolution, it will have smaller size, smaller dimension compared to input?
Sorry, what can you repeat?
So I have written here, I'm not using any padding here. Okay.
Yeah.
Since I'm not using any padding, after performing convolution operation, the output which I'll be getting, that output dimension will be smaller than this input,
Yeah, it will be smaller.
because I won't be able to apply that filter in the corner pixel, right?
I mean, I'm saying it will be smaller because, like, looking at the output W0 by running the numbers, most likely it is going to be small, right? Because we are not applying padding. Yeah, you're right. If we had applied padding, then the
Yeah,
dimension would have been same to the input.
correct.
Yeah,
That's what I was
Right.
looking for.
Sure. Yeah.
That's what I was looking for. Okay. So can you tell me what will be the dimension of this output after applying convolution by this filter? Can you quickly do the math and let me know?
$28.
How 28?
32 minus 5 by 1 plus
32 minus 5
by
by 1 plus,
plus 1.
plus 1. Exactly. Okay. So this after convolution, this is the output you are getting, and the dimension is 28. Now I'm using total 6 such filters, such kernels, right? So similarly, you will have total 6 output because I'm using 6 kernel.
So when you say you're using 6 kernel, what do you mean by that?
So right now, whatever we have seen, that is for one kernel, right?
But
So-
why are you using 6 kernel? Are you talking about those 6 type of kernels where
Yes.
they do different things, right?
Yes,
That
yes,
when you
yes,
say, okay,
yes.
okay.
One kernel may be learning your edges, one kernel may be learning some other feature of it. So likewise, I'm using total 6 different kernel.
Yeah,
Okay.
yeah.
So you'll be having total 6 such 2D matrices.
Yeah.
Right. So till this part, any confusion? So this is what we will be getting in convolution layer, convolution layer 1.
Yeah.
Six 2D matrices stacked together. The dimension of each matrix will be 28 cross 28.
Yeah.
Okay. And now can you tell me what will be the total number of learning parameter till this part?
You mean at the pink part, right?
Yeah,
Convolution layer
yeah. So whatever thing that we have covered till now, till that part, what is the total number of learning parameters? You have to do a very small math. See, my dimension of kernel is 5 cross 5.
Yeah.
Right. So 25 weights are there. Right. 25 and total 6 such kernel I'm having. So total number of learning parameter is what? 25 into 6.
Yeah, that's 150.
That's 150. Right. So till your convolution layer 1, I'm having total 150 number of learning parameters.
Yeah, that's correct.
Now I'll apply some nonlinearity to it. I'll apply ReLU, but that will not change my dimension, right? So that's why I have not included here application of activation function. You can, again, I'll say the same thing. Just consider that I'm applying an activation function, which is identity.
So you're saying that you're applying a max pooling function, right?
Yes, but before applying max pooling layer, we have to do some nonlinearity also, right? You have to apply activation function also. So again here, since activation function is my identity, that's why I have not mentioned it anywhere here.
No, but then you're reducing the dimension to 14, right?
I haven't come to this part. I'm still at this part.
Okay, so at that layer you are applying the activation function,
Hmm.
nonlinearity, which is some activation function.
Yes.
And that what is that doing? It is giving some output, right?
Yes, that will give some output, but the dimension of my matrices will not change. Only the pixel
Yeah,
value
they
might
will
change.
not change. Correct, correct. They will not change.
So that's why I have not written anywhere about about activation function. Okay.
So activation function anyways will never change the dimensions of the matrix, right?
Yes.
It will only change the values of the matrix.
Correct. But the reason of mentioning that point is, please do not think that this is the only thing happens in neural network. This is the thing happens in neural network along with application of activation function, which is not mentioned in this diagram, because anyway that's not going to change your dimension. That's why there's no point of adding activation block also here, because unnecessarily it will clutter the figure. Okay. All right. Now I have to apply a pooling operation here, right? So what I'm doing is, I'm for pooling also I need a kernel. So the dimension of that kernel is 2 cross 2, right? The stride is 2 here. So I'm jumping my pixel by factor 2. Okay. And again, I'm here total having 6 number of kernel, right? So what will happen? The feature map that we have got here, it will just simply downsample. And the dimension of this feature map will just reduce by half, because the filter size is 2 and stride is 2. Are you able to understand here?
Yeah, that I understood. How it came from 28 to 15. But then, what else we are doing there apart from just reducing the number of dimensions? What else we are doing?
Nothing. We're just reducing the dimension. That's why you see the number of learning parameter here is 0, right? Because we are just putting an arbitrary filter there. We are downsampling it by.
Oh, but why it's 0? It is still it will be like there. It was 5 cross 6, right? So the 5 cross 5 was the kernel size. So here the kernel size is 2. So it will be 2 into 2 into 6.
Yeah, but here, see, here I was performing a convolution operation. That's why I was interested learning the weights of those kernel. Here I'm not doing any convolution operation. Here all I'm saying that actually here I'm not actually, it's not even a kernel. It's just that I am taking the highest value of 4 neighborhood pixel.
That you are doing before applying the max pooling function, right?
I think I need to okay. Till this part it is clear.
Yes.
Okay. Now what I'm doing is, here let's say that this is a 4 cross 4 grid.
Yeah.
Okay. In this stage what I'm doing is, I'm just applying here. Don't think that this is a kernel. This is some extensile you can consider, right? What I'm doing is, I'm just taking the 4 neighborhood pixel. Okay. I am picking the highest value out of it, right? Here let's say that 1 2 3 4 5 6 7 8 9 10 11 15 16. Okay, this is 6, right? I took this box. What is the highest value? 6. So I extracted 6 out of it. After that, since I said that I'll be taking the stride of 2, I'll be putting this thing here. I'll be putting my box here. I'll be taking the highest value. Then I'll put my box here. I'll take the highest value. Then I'll put my box here. I'll take the highest value. Right, so this entire operation is called pooling. We are not doing any convolution in pooling layer. We are just picking the highest pixel value of among the neighborhood pixel. Is it clear now? Hello?
Sorry, I was on mute. So you're saying that in the pooling layer, we are not doing any convolution. We are just picking the highest pixel.
Yes.
That's what you're saying, right?
Yes, yes. So there is no learning involved here. I'm just simply taking the highest value from by 4 neighborhood pixel.
Okay. It is clear now. Yeah. So the parameter will come only in picture when
there's a convolution operation.
And we will know that, right? That when it is a convolution operation
Yes.
and when it is not a convolution operation. For example, in pooling case, we know that it's not, like as you explained.
Yes. Yes.
Okay.
Okay. So this is just downsampling my input image. Okay. So like the way I have downsampled one image, similarly, you have to perform this downsampling in all those 6 matrix. So this is a reduced version of this one.
Yes. And with the highest intensity pixel values.
Yes, highest intensity pixel value. Okay. Now what happens? Now again comes the convolution layer, right? So now the learning will happen. Now I have defined my kernel of size 5. Okay. And I'm total using 16 such kernel. Okay. And the same thing will happen again. What happened here? Now the number of learning parameter will be 2400. How 2400?
5 into 5 into 16.
Yes. Right. That's why you got total 16 2D matrices. Okay.
Yeah.
Again, you will do downsampling here. Downsampling using box 2, stride 2. So this will just reduce the dimension of your image by factor 2 because I'm using stride 2 and box size 2. Okay. We have proved it also here by taking this example. This was 4 cross 4. Now my output is 2 cross 2. Okay. So now finally, after this pooling layer 2, I'm having total